Now, having finished structure analysis, our next activity is going to be the design of the various structural elements, and this includes beams, or rather slabs, beams, columns. Right. So let's start by designing the slabs. Okay. So we have two different types of slabs. We have the cantilever solid slabs. We have the solid slabs and the ribbed slabs. Okay. So to design a slab, why we started with slabs is that we do not want uh, to design a beam and then later come back and find out that our slabs are insufficient and that we have to make adjustments to the geometry of the slabs. This will have an effect on the loading imposed on the beams. Okay, hence it will affect the beams, which also in turn affect the columns, which also in turn affect the foundation. So we shall design from up to down. Okay, so top to bottom. So you start by designing the slabs. Then afterwards you design the beams and columns as a frame. Like you can design them together. Okay, so I prefer starting with the columns. Then I go to beams. Okay. Then from there, we shall go to what? To the foundation. And then finally the staircase. Okay. So before you design any member, you have to first perform a few adjustments to the settings. So let's go to settings, slab design settings. Okay, and here this one, this parameter we already saw how to change it. Concrete cover for slab shall use 25. Then so if you want to now to calculate cover, you go to Eurocode 2. Open Eurocode 2. Okay, you open Eurocode 2. So open Eurocode 2. Section 4. Section 4. Okay, so under this section 4, durability and cover to reinforcements, you can try to follow. Okay, try to follow the general procedure. Okay, so usually we categorize cover into two. The cover computed from Eurocode 2.1.1, which is this. So the cover due to durability, okay, or exposure, or rather environmental exposure, then the cover due to fire. Okay, so for computing cover due to fire, we saw that when we are performing preliminary sizing of the members. Okay, so that one you use Eurocode 2, part 2. Okay, Eurocode 2 part 2, which is this Eurocode 2.1.2. Okay, where we have minimum dimensions of structural elements. So the cover here is the cover due to durability is measured from the outer face of the concrete member to the outermost edge of the reinforcement. For instance, a stirrup if it's a beam, okay, what we call the nominal cover. Then the cover due to the fire resistance is this what we call the axis distance is measured from the outer face of the member to the centroid, okay, the centroid of the longitudinal reinforcements, okay. And in most cases, this cover governs for columns, whereas durability wise, the cover for anyway, I don't want to make conclusions, but you can follow the procedure. You can compute the cover from the other side due to durability, then compare it with the nominal cover. So you have to reduce this cover. You have to deduct this axis distance. You have to deduct the half the longitudinal reinforcement diameter and the stirrup or link diameter. Okay, the balance will be what you compare with the cover due to durability. Okay, so let's not go deep into that. Okay, and then we shall here we shall adjust cover, then this which we changed last time, then the bar size. Okay, the bar size. So minimum bar size for our design shall maintain 10 for slabs. Prefer using 200 as the maximum spacing of reinforcements. Okay, due to crack width related purposes. Okay, from there we shall also adjust settings for the ribbed slab. This one we get it from beam design settings, then rib settings. Okay, so I prefer design shear force. So it's more economical to design for shear force at a distance d, or rather effective depth, from the column face or from the support face. So this for the ribs, the support in this case will be the drop beams or the main beams. Then shall put 25 as the cover as well. Okay, 25 everywhere on all sides of the rib. Then with the reinforcements, we shall also maintain. Okay, so 10 is not listed here, but let's first save. Okay, so we have to first select all the reinforcements available in our country, available for design or for use actually in our country or in your country. So to do that, we shall go to analysis, building analysis. Okay, so go under material, edit materials. Okay, so we shall under here we have two tabs. The one for default material, which accounts for the superstructure. Then we have foundation flow. Okay, let's start with the foundation. So let's edit to the grade of concrete. Okay, so here, based on your exposure, if you have if your project has a geotechnical investigation report, you have to calculate for the grade of concrete. There's a minimum grade of concrete based on the soil conditions. Okay. In most cases, when the soil is contaminated with sulfates, when your soils are have high percentages of salts like sulfates, chlorides, these which react with the cement and compromise it. Okay, they react with the cement in the concrete and compromise its integrity. So you'll have to use a stronger grade of concrete. Okay, so you shall use a normal grade now in our country, which is C2025. Okay, you shall apply it to all members. Okay, unfortunately, we here are only having one member, which is the foundation. So do the same to the grade of reinforcements. For the grade of rebar, you shall use 500. Okay, apply to all members. Go to the links, apply to all members. So in case your foundations, for instance, is made up of foundation beams, piles, you'll need links. Okay. Then under foundation, still go to rebar diameters. Now under rebar diameters, first unselect all the bars, then deselect all the bars available in your country. Okay, so shall start from 8, select 10, 12, 16, 20, 25, okay, and 32. All those are available in our country. Do the same, just make the same selection. So for links, we shall just usually need 8, 10, 12, and maximum 16. Okay. Then under soil, in case you're doing finite element analysis, you'll have to define the soil parameters. Okay. So for now, you don't need to do this because we shall use a presumed bearing capacity to size our foundations. So having got done with the foundations, let's go to the superstructure. So let's start with the grade of concrete. Choose C20, apply to all members. You can see it applies to all members. So we'll change also the grade of, use C20, 25, apply to all members. Then since we don't have any steel, structure steel, we won't bother adjusting the grades of structure steel. Okay, then the reinforcement, we shall maintain this grade 500 as our yield strength. Then for the rebars, shall do the same, 8, 10, 12, 16, 20, 25, 32. Okay, so do the same for walls. Okay, 8, 10, 12, 16, 20, 25, 32. Okay, then longitudinal. Okay, so these are the intermediates, both longitudinal and horizontal for the wall. So we shall 8, 10, 12, 16, 20, 25, 32. Then do the same to the horizontals, 8, 10, 12, 16, 20, 25, 32. So keep doing that for beams. Okay, it's only after selecting the different sizes from this side, okay, that those sizes will appear in your settings with the different member design settings. Okay, slabs. Then ribs, do the same. Then links, 8, 10, 12. Okay, let's stop at 16 for the links. It's okay. So that is it. So we are done with that. Okay. Alright. Now we can now go back. Can go back to slab design, steel bars, and choose the 10. Okay. Okay, for our ribs, sorry, ribs. So beam, rib setting, parameters, so shall use 10 as our minimum and 10 as our maximum. And see that under the options given, only those bar diameters that we selected the other side are listed. Okay, then with the link, under normal circumstances, we don't use links in our in slabs, in ribbed slabs or slabs less than 200 mm thick. Okay. So that is stated under section 6 of Eurocode 2. So you can go and read about shear in slabs. So open Eurocode 2, look for shear in slabs. You'll find that statement there. Okay, so steel pattern, shall choose pattern number 3. This is simply detailing guide or rule. Okay, so basically that is enough. Same settings will apply to the beams as well. Okay, so after adjusting our settings, we are going to draw what we call slab strips. Okay, draw slab strips. So under slab strip properties, we have an analytical strip, an FS strip, and a minus strip. Okay, under the minus strip, you specify the reinforcements and carry out checks later. Okay, we can try that. Okay, since we already made adjustments the other side, we can leave out actually the minus strip. Let's press escape. So we shall use the analytical strip. F is finite element strip. This is used when you are using finite element analysis for slab design. Okay, so we shall use analytical strip. Shall choose analytical strip since we are uh, we are not we are not we are not we are not using finite element. Okay, then from there, these are end conditions of the slab of your strip. Okay, means slab, continuous slab. This means continuous end. This is okay. This means the slab is non-continuous. Then this means cantilever. Okay, so we are going to do a strip from. So when we look at our ribbed slab, actually the most critical strip would be here. Okay, this slab has a higher span, has a longer span, so it will deflect more. And given that the slabs are having the same loads, okay, the strip here So we shall check this and also this single span panel. So I'm going to draw two strips for the ribbed slab. So let's first set end to end. Okay, non-continuous, non-continuous, because this slab this panel is not continuous on either end. So we shall do strip, press Ctrl to make it horizontal or straight, to make it straight like that. So this is strip x1, as you can see, x1. So I'm going to draw another one here. Same end conditions. Press Ctrl like that. Okay. Alright. So from after that, we are now going to run analysis for our slab. To do a slab analysis, we do it under design, or you can simply select the two strips, right click. Okay, now that will not work with more than one strip. If it was one, you would just right click and choose with slab analysis. Okay, or you just come here, right click on this, then choose with slab analysis. So it's going to produce a report afterwards. Okay, which report you can export. You can export this report to your folder. Okay, so read slab. Okay, for now we can leave it since this is not the final, but we shall export all these reports and append them to our general structure design report. Then after that, you can still go back here, right click and choose with slab design. Okay, then you're simply just going to tap batch design. So under design, under beam and column reinforcement design, we have three options. The first option is check steel, select new steel. So this one will check the capacity of your structure member, and if it is insufficient, it will add more bars. Okay, to add more steel bars to it. Then this option, don't select, check but don't select when the previous ones are insufficient. This one, you tell you that the section is insufficient, but it won't modify it. Then here, reselect all bars. So reselect all bars, it means the entire section is going to be redesigned based on the current reinforcement settings for that particular for either the beams or columns, whatever member you're designing. Okay. So when you're carrying out a fresh design, this will be the best option. Reselect all bars. Okay. So from there you can see that our rib X1 is utilized 70%. Our section is utilized 70%, which is good. The next two 80%, which is good. So the X implies there is something that needs investigation. Okay. So you can see that our section here, our rib fails deflection for the single span. Okay. It does not fail that much, but it almost fails. Okay. Then here, this is the area required, and in blue, area required. Okay. Then of course this is what is provided. So you just simply get the number of bars, or you could just add this plus what is required. So for the top steel here requires 0, but we provided 157, which is this is the area of 2 bars of T10 of 10 mm diameter, sorry, of H10, okay, which is also the same as 24.52 plus this, will give you this, okay, 24.52 plus 132.56. Okay, so you can see that you get 157.08. So this is the excess. This is the excess of what is required. So measure this rib requires more steel at its mid span. So the steel is sufficient for bending, but the section is insufficient for deflection, which we can also improve by increasing the bar size here to say 12. Okay, you can see when you increase to 12, it passes. Okay, so we can either do that. Let's first check the other strip. So this one is also failing in deflection. Okay, so it needs 0 bars here, but here at 0 bars at the ends. That is for the top steel. So we only need short bars across the middle beam, 3 of them, but of 10 mm. Then down we need 2 bars of 10, although they fail deflection in the first span CE. 10 fails deflection, but 12 passes. So when we provide two continuous bars of 12 mm, the beam will be, or the rib will be safe. Okay, so it will look nice, it will not scare the occupants. Okay, because it will not have deflected that much. Okay, so we can first leave the 10 mm. Okay, so we can try an option of the slab beam. Can provide slab beams, and provide this, can try to provide the slab beam here, and also the slab beam here, and we see whether it will work. So to do that, go to beams, just model beam of size 300 by of course 200. Since it's a slab beam, it will have the same depth as a slab. So you're going to draw that beam from here to here. Okay, our analysis is what invalidated. So we are similarly, we are going to create a grid here. Just offset this. Okay, I need the exact mid span. That will be, this is 31850. Offset. Okay, not 180. Yeah, 1850. Okay, press function key F2 to bring the box, then enter. We shall call this grid E prime. Okay, I'll stretch it from there to here. Okay, so we are going to transfer the same properties. Okay, in this slab, like okay, so now let's go back and cut out our analysis. Also, but before that, For that, we need to come back here where we take slabs. Okay, where we set slabs to define rigged diaphragm. Not We need to untick all stories, and we also untick the roof. Okay, shall untick the roof. Why? Rigged diaphragms are refer to slabs, reinforced concrete slabs, okay, that are rigged enough in their plane, okay, to tie all the vertical elements, for instance, columns and shear walls together in such a way that when there is lateral movement, that's the entire building moves as a whole at that level, that floor level. Okay, so at the roof level here, we don't have a slab to do that, to achieve that, so we shall untick the roof. So at that level, it means there won't be anything to do what? There won't be any structure, any rigid diaphragm or any stiff horizontal element to tie all the vertical elements together. So the wind loads, any wind load that hits the building at that level, it will simply be taken up by the individual elements. Okay? Yeah, that is a simple explanation I can give. Or the wind will actually just go to the roof, and later from the roof through the trusses, it will now be transferred to the individual columns supporting the roof. Okay. So and then also I want us to put here a 1 under slab stiffness coefficients. Okay, so that the full stiffness of the slab is put into account. Okay, then you can carry out our analysis once again. Okay, so let's go back and now redesign our ribs and see whether there is a change in the deflection after given that we have what provided slab beams. So come here, rib slab design, then batch design. We select. Let's see if there is any change. Still failing. Okay, still failing. Same applies to this. Still failing. Okay. Okay, so what we shall do? Shall remove them and just adjust the what? Or actually, such beams may work after carrying out finite element analysis. Okay, this analytical strips may not work, but finite element analysis may try to solve the issue. So you can give it a try. Okay, so go to your strips convert them into go to properties, convert them into FE strip. Then under FE, come to FE tab and choose the ribbed slab. Then update. Don't mind the pop-up. Do the same to X2. Choose FE. And this update. Okay. Then from there, just go to analysis. Go to finite element for analysis. Ensure the store of interest is selected there. Okay, just do one thing here, change the stiffness factor to 0.25. Okay, because if you don't, you may get a notification or a pop-up, which is this. So for beam slab systems, we recommend to reduce the slab stiffness to typical value of 0.25, so that beams are relatively much stiffer and slab load transfer to the beams is maximized. Okay, so let's do that and we repeat. So like that. From after doing that, you generate the model, your slab model. Actually, something we forgot. We forgot to. Okay, let's first check. The rib before we add in the slab beams again. So start out with slab analysis. Okay. One thing we didn't do. Let's go back to FE. Okay. Let's analyze. Generate a model. Close. Go to analysis post processing. Okay. Okay. So don't mind the FE model. Simply close here and get it be asked whether you want to transfer the FE results. Okay. So transfer slab FE analysis results, including strips. Then you say okay. Then can close. If you want to okay, for now let's close. Okay, so now go back to rigged slabs, right click, rigged slab analysis design. Okay, so these are the results, the analysis results for the ribs. Okay, so we have strip 1, we have the support moments at either end, 3.3 and 1.9, then the shear forces and the span moment of 4.9 at the bottom. Similarly for strip 2, we have this one has two spans, okay, with the intermediate with the end span at the support. The end support as having 4 kilonewton meter. Then at the intermediate support has 9.5 on the left and 9.1 on the right. Then 0 at the extreme end. Okay, then these are the shear force and bending moment values at the mid span. Okay, so you can also save this as in a Word form for further pending to your general structure design report. So we can now design our slabs again. Okay, so you can see that finite element is more realistic. Okay, so finite element analysis is less conservative compared to the to the building analysis or to the normal analysis. Okay, so this is actually the other one is referred for the slabs to be referred to as tributary area method. Okay, so here our ribs are safe in deflection. Same applies to this. Why? The reason for that is that uh, the finite element analysis considers fully the stiffness of the entire slab, okay, and designs the entire slab as a whole, okay, and it also considers the stiffness of the interconnecting members or the supporting members, okay. Yeah, so but we shall just rely on it for the slabs, and we shall save those as our analysis results, okay. Shall save the generated results as our analysis results. Okay, so I want us to try putting a slab beam, and we see whether we shall have a deflection here of 28.74. Okay, a span to deflection ratio of 28.74. Let's try doing that. Let's see whether it will reduce. Okay, so let's just try it out with this one slab. So put here 300. Put here 400. And put here 200. Then let's do our slab. Then carry out the finite element analysis. Once again, generate model, close, analysis, post-processing, close, transfer results to the strips. Okay, let's do now the strip analysis. Okay, consider that even the span moments have reduced. Okay, now let's carry out the design. Batch design. Let's check our deflection. Okay. So there's literally no difference. Yeah, so there is no difference in the deflection. Okay, so I'll need to do further study about this because the truth is the slab beam has uh, contributes to increased stiffness of the slab at this point. Okay, that is the reality. Okay, so let's run our building analysis again. Okay, but before we do that, let's also design the solid slabs. Okay, so since our balcons have the same cantilever length, shall just uh, design one. Shall design one. Shall choose analytical strip. Analytical strip. Okay, let's maintain FE. Oh, okay. Let's do analytical. Let's do analytical. So we are going to start our strip from here, the cantilever end, up to this is a continuous end. So you shall choose continuous. There's a slab on the other side. That's why I'm choosing continuous at the end. Then and so that once your slab passes deflection checks, it automatically gets designed. Okay. Yeah, so but regardless, you have to carry out slab analysis and design. So come here, right click, slab analysis. So you'll get there. There is oh sorry. We are meant to come to slabs here, then slab analysis and design. Then you shall set delete and reselect all bars. Okay, so these are the results. Okay, so support moment. We have a moment of 6.3. Okay, and the reinforcement required is simply 196.35, but what is provided is H10 at 200, so it is sufficient for the balcony. Can as well carry out deflection check for the slab, deflection check, and crack width. Okay, shall apply it only the slab strips in the current story. Shall limit our cracks to 0.3 millimeters and check deflection regardless. Then okay. So all these reports being generated can be saved for later appending in our general report. Okay, so deflection wise we are good. Our crack width is 0.14, which is still less than, it is within the limit of 0.3, so we are safe. So you can do the same to the tank slab. Okay, so we are going to design this and this. So draw two strips end to end and cantilever to slab. So you can see that the same reinforcement are sufficient. Okay, let's analyze this strip or design. Okay, we require 156, maximum is 196, and we are safe. This is what is provided. We are safe. About this, right click, strip design check, 196. So we are safe. For H10 is sufficient for our slabs. Okay, everywhere H10 is sufficient. Okay, so you can as well check deflection, X3, X4. Okay, slab deflection check, 0.3, current story, check deflection regardless. But usually by the time the program accepts the reinforcement, the slab has already passed the deflection check. Okay. Okay. So we are good to go. So we are done with slab design. Okay, we are done with slab design. We can proceed to frame design, that is beam column. Okay, you can activate your design status under this button to see the status, how the progress of your design. So you go there under visual integration, choose design status here. Okay, you can see that the white indicates our model is not yet, our frame is not yet designed. Okay. So similarly, before we design the frame, shall go to both beam and column settings. So beam, story beams, we make the adjust settings. We adjust the necessary settings. So we shall choose 25 as our cover for the beams. Then for the reinforcements, we shall maintain 16. For the load carrying floors, okay. For the floor beams, now in other words, shall maintain 16. Then 8 for our stirrups. Okay. Okay. Type of stirrup shall use standard. Design link spacing at support. No, I don't want. Okay, save. Okay, we go back to column design settings. So here under here we shall go to steel bars and adjust the longitudinal bars. So we shall still use 16 as our bar size for the columns. Okay, for the walls we can maintain maybe 10. So we don't have any walls here, so that this won't apply. So let's focus on the columns. And for the cover we shall use 30. Okay, so we are using 30 in this case. Then for the links we shall maintain 8. Our maximum spacing will be 200. Okay. Provide links through beam depth, no. Create support regions for links, no. So bar selection, bar size maximization. Okay, save. Update concrete cover for all columns. Yes. So we're going to go back to analysis, building analysis. There's a setting here. Beam section shall use flanged beams. Okay. Yeah, we are going to utilize the fact that we have a slab on top of our beams and they are cast in situ. Okay, so part of the slab will act as a flange to the drop beam. Okay, and it will provide more compression resistance at the mid span of the beams. Okay, then rigged zones. Rigged zones. When you choose maximum, it would mean the rigged zones in this case are the columns. Okay, when the columns are rigged, it means the beam spans will start uh, from the face of the column, and this is uh, this is actually more realistic for reinforced concrete columns. Okay, or you can choose reduced to allow for joint column beam joint what flexibility. Okay. For now, let's choose none. Let's go with none. This is more conservative. All right. So let's do analysis. So actually under here you can actually tick design. You can design the columns and beams immediately after analysis at once. Okay, and then as I said, we shall reselect all bars. When it's our first time to design those given members, we shall always reselect all bars. Okay, next time we come back to check when we are making changes to our columns and beams, we shall not what? Shall either tick or not tick here. Okay, so we are done. The design is complete. The analysis and design are complete. Okay, so when you look at our model, you can see the design status of the entire model. Okay, so red means fail, yellow is warning, like now. Okay, then this color orange is expired analysis. Then green is it means okay. So green means the design is safe. So we cannot proceed with detailing until when all these frame members are green. Okay, so from starting right now, we are going to size and reorient each column one by one till when all columns pass a design. And from the columns, we shall go to the beams. So let's switch to plan view and head to the lowermost story and activate activate design status. Okay. Okay, so I want us to load the our floor plan on this level. Okay, so that is our floor plan. So our column orientation has to match with the floor plan. We do not want our columns to protrude into our spaces. Okay, that's why I had to uh, bring up the how to re-import the floor plan. So let's start with this column. Right click, choose column section design. Okay, so I'll start by choosing the design method as bar spacing maximization. Then call out interactive design. Okay, after doing that, look at the load combinations here. These are the analysis or the analysis results. So under combination 7 highlighted red is the design combination, the critical combination. Okay. Finally, we have the axial force, the bending moment about axis 1, bending moment about axis 2. Okay, shear along axis 1, shear along axis 2. Okay, and this is now the load combination name. You can see that this column uh, experiences significant bending at its bottom. So the column experiences significant bending at its bottom due to along direction 1. Okay. Okay, but so before we proceed, I want us to make some small adjustment in the wind load. Okay, and I see whether it will have an impact to the analysis result. So before we proceed, I'd set our story height here, the bottommost story height as 1.5, which is correct. But then the wind load calculator assumes that this height is actually from the ground level. It assumes that our ground floor is raised by 1.5, okay, from the ground level, and it utilizes all this length to calculate the wind load that assigns to the ground floor level. So I want us to first change this to 300, okay, as the plinth height for our ground floor level. Okay, then we go back and we compute the wind loading. Then we shall come back and adjust later. Shall maintain 18 here. Then change this to 0. Since we are not sure. Or we can actually ask Google to give us tentative values for our area here. Okay, so uh, okay, so we shall use 120 meters. Okay, so you see, shall use 120 meters. Then our x, this is the height of this. Then LOU will be 900. So LOD is 1000. Then x is 500 meters. Sorry, hello is 900. This is the 900. LOD 1000. Then x is 500. Okay, so this area, our area is surrounded by hills, okay, which affect the flow of wind around the buildings are the surrounding buildings. Okay, so these are our. Consider now the height based on compute the wind at story 1 is 0.3 meters. This is more realistic. Okay, this is more realistic. So now let's apply our wind load to the building, as you can see. So from there we can now go back. After applying the load, we can go back and put back our original values. Then we can run building analysis and design again. Before we design the beams, let's go back. Let's go to settings, beam settings. Okay. Well, actually, not settings, but beam design. So concrete design, beam reinforcement design, story beams. Ignore that. So we are going to group our beams that those that have similar length, similar spans and length shall be designed as one. Okay, so we shall have the same details for our similar beams. So this will cut across all stories. Okay, so go to grouping tab. Under automatic grouping, choose group all similar axes. Then yes. Okay, that is done. So from there we go back, close and go back to analysis, building analysis. Then tick column and beam. Still, you are going to reselect all bars. So start the analysis and design. Okay, so once again, let's head back to our interactive design. So this is our column. Let's reload. Let's reload the plan. Okay, so right click, column section design. Okay, so the moment reduced slightly from 17 to 16. Okay, so moment about axis 1 or moment about grid 1, it means the beam causing this moment, okay, is along the beam transferring this loading to the column is along grid 2. Okay, so bending about 1 means the curvature, the column is actually bending towards 1, towards 2, and bending about 2 means either the column of beam, the beam causing that is along 1. Okay, so when we see a moment here, the best thing to do is to adjust the dimension along the other direction. Okay, so we shall adjust the dimension along 2. 2 is the y-axis. Okay, so we are going to increase our section going downwards like this. So we are going to increase this column's dimension downwards. So we shall try 300, update. Okay, when you saw okay, you can see that the column increases but it pops out. So we are going to provide an eccentricity. Okay, easy. 50, an eccentricity of 50. So we are going to push this column downwards by 50. Sorry, column section design. And since it's downward, we shall assign a negative to it. Then update. You see. Okay, now let's design check it. So to check check to check our new section, just click on interactive design and it will carry out the design. So once the area supplied is provided, okay, and the area required, the area supplies once the area supplies is more than the area required, you're good to go. Okay, so we need three bars of 16 millimeter, 6 bars, sorry, of 16 millimeter diameter. Okay, and we are done. After that, we are going to apply the same section from down to the top by just right clicking. So we're going to apply the same section to all the upper stories. So I'm going to right click, go to member tables, choose column table, then tick all stories here. Okay, since we are having the same column label, so this only works when all the columns in this position at all stories are having label 1. Okay, ground floor column 1, first floor or floor 1 column 2, floor 2 column 3, roof column 1. Okay, column 1, sorry, column 1. Then from there you can batch edit this dimension B2 to 300. You also edit its eccentricity to negative 50, like that. Okay, then from there you can now see when you navigate this various stories, you can see that the column is okay. It was ending at roof. So we are good to go. Okay, so you have to do the same to all stories. Shall design these ones. Shall run another analysis and design. Okay, to capture. To define new reinforcements for the top the upper floors. Okay, let's do the same to this column 8. So column 8 is typically an axial load column. The moments are small, but still the moment along 2, moment about 2 is bigger, so we shall increase the dimension b1. Okay, so shall change this to 300. Okay, since the wall is there's a wall in this direction, so we shall push the centricity this the negative in the negative direction, so negative 50. Update, then interactive design. So there's a warning. Actual load is exceeded. Section sizes must be increased. Shall increase to 500. Simplicity is usually the simplicity will be 100. Okay, so the bigger the column, the more it protrudes out. So then interactive design. So 500 is sufficient. It gives us 8 bars of 16. Okay, then say okay. So apply the same section to the upper stories. Right click, choose member table. Select the column. Right click, member tables, column table. Choose all stories. And, batch, change the dimension B1 to 500. Eccentricity E1 to negative 100. Okay, so we are going to do this to all the columns. Okay, we're going to quickly do that the same to all the columns. So here we're requiring a lot of bars in a smaller section. So it's better we just increase the section to 500. So 6 bars. So here let's do this column. So I've temporarily turned off the beams so that I'm just left with columns and my reference drawing. now you see there's a door opening here, so we do not want this column to encroach on our door opening. Okay, the architect will be mad at us. So let's push it the other side. So we shall give it a positive eccentricity of 100. Like that. Okay, so uh let's do the same to this. All right, let's check this corner column down here. So this one it's going in this direction, but we have a whole other side, so we can maintain it centered. In other words, we shall provide zero centrist. Okay, so let's try 300, sorry, interactive design. 10 bars, quite a lot. It is safe, but many bars. Okay, 500 is 6 bars. This one balances out. Good to go. Generate it to upper stories. Done. Keep saving your work, okay? Endeavor to save. Okay, but maybe uh, this orientation might affect the top story, okay? The tank story. So this column will pop out at that level. Maybe you can push it inside there. And push it inside member tables, column table. So we shall give it a positive eccentricity here of 100, like that. Makes sense. Okay, so let's do the same to this. Okay, this one 300 is sufficient. Shall give it a negative eccentricity of 50, like that. Then generate it to the upper stories. Okay, so we are left with 4 columns. Let's start with this. So 300 there is sufficient. Give it an eccentricity of 50. generate two member tables, column table, generate two other stories. Come to this, do the same. Okay, finally. Okay, two to go. Two to go. Two columns to go. Sorry. Okay, so we are done resizing and resizing and orienting the columns. Okay, so we are now going to run our analysis and design check once again. Okay. Okay, so we shall go to analysis, building analysis. Show it is tick column, pick beam, reselect all bars. Alright, now let's see if there are any fading columns. So no fading column at any story. So all columns have passed. Okay, you can check under concrete column design and check the utilization ratios. Okay, and see that is full maximum utilization. This is at flow 1. Can filter out stories. Okay, let's filter out the tank slab columns. Okay, 50%, 51% maximum utilization, meaning you can even reduce. Okay, and reduce the diameters of those columns of the bars at that level. Okay, to 12. And reduce the diameters to 12 at that level, so that you optimize the sections. Okay, you are trying to save the client his money by doing this. Okay, let's see the roof level. Maximum is 57. Can do the same. So ideally, we can just redesign this entire story using 12, but we have a 71 somewhere. Okay, so we shall further optimize when we come to the detailing. When we come to the detailing stage. Okay, but you can simply come here and choose 12 under the settings, the column settings. Then you run design with only this story selected. So you deselect the bars. Okay. Consider the 12 works everywhere. Okay, we shall maintain 12 from the roof to the from fourth floor to the tank slab. We shall be using H12. Okay, let's see fourth floor. Okay, fourth floor downwards shall maintain. We can maintain 16. Can maintain 16. Can maintain 16 for the rest of the stories. Okay, so that is all with column design. Okay, then you can switch to can come concrete design beam, then story beams. Okay, so here it's a matter of checking out the failing beams. Okay, so we shall first isolate the floor stories, that is first floor to fourth floor. After that, then we check one by one. You can see most of the beams are passing except a few. Can even filter out failed members on top of filtering out stories. Okay, so let's start with this group 5. That is a beam having 4. It's a beam group having 4 similar beams. Okay, so the failing is not due to section capacity but to spacing of reinforcements. Okay, you can reduce this to 1. Okay, or simply we can just provide 3 bars here on top. 3, 2 plus 1. Or 2 bars, 2 bars. Like that. That one works. Then can layer them. So select this, put it at layer 2. Same applies to this. Or you'd simply then with that it's the same thing. 2 bars down, 2 bars up, and short bars. Okay, this one requires 2, this one 1. So move those bars to layer 2. Okay, we have a maximum of 3 layers of bars. Do the same to this. This is a single span, so I'll just provide 3 bars on top. Or we layer them like that. So there's not much work to do in beams. Most of the work is in columns. Okay, layer 2. Okay. So this is a heavily loaded beam. So it's requiring 3 bars up. Okay, so let them be continuous even to, they cantilever. Same applies to this. Okay. Okay, let's maintain 2 here. 2, that is okay. 2, then with one extra one to make 3. Extra one like that to make 3. Layer 2. This one's also layer 2. This one's also layer 2. Like that. So even up, you're going to have 2 continuous bars and an extra one at the top. And we are done. So this is all with the floor beams. Okay, you can filter out then the roof. Okay, let's start with the tank slab and do the same to it. The tank slab is having, there's nothing displayed, which means it's getting its reinforcements with the other, with the downer beams. Then let's see the roof. The roof, I want us to use 12. Okay, let's see. Okay, roof. Okay, this is the level where we are Okay. Tank slab. Let's go back to tank slab. Add selected failed members. Okay, this is it. So we have a maximum utilization of 63. So this implies we can actually use 12 as well. So go to settings, choose 12 as minimum and maximum. Then just do batch design. Deselect all bars at that level, like that. Okay. So I use 3 bars of 12 at the top. Oh, we can, for this beam, we can maintain 16. Seems to be a bit critical. Then let's see this one. And we can maintain the 12. Okay, we are done. So roof, we go to the roof. Redesign the roof with 12 as well. Okay, so this is our ring beam. So we shall simply provide 3 at the top for this. And so we shall represent most of these beams when it comes to detailing with sections. We won't detail each and every elevation. So far we should have 2 sections, one with two bars of 12 up and down, then another section of 2 bars of 12 down, and 3 bars of 12 up. Okay, so this let's maintain, since this is a cantilever, let's maintain 16 up, 2 16s up. And see it is over deflecting. Okay, actually 3 16s. 3 16s up and 2 12s down. So this is a critical roof beam. Okay, so 3 sections of 3 sections at the ring beam level. Then let's go to the ground floor level. Redesign it with let's redesign it with 10s. T10. So our soils are not that bad. Okay. Yeah, so our ground beams, our ground floor beams will rest on plinth walls which are stiff enough, okay, and they rest on firm soil, so they are stiff enough to take up, okay, or to resist all deflections at this level. Okay, so let's try 10. Okay, so don't mind about this for that for the ring beam level. Oh, let's actually use 12. Okay, 10 might be small, quite small. Let's use 12. Batch design, we select. Okay, so regardless of what we are seeing here, we shall provide 2 bars of 12 up and down for our ground beams. So we are done with beam design. Okay, so close. You can now see that our entire model is green. The entire frame is green. Okay, so after designing the spark structure, the next step will be design of foundation. Okay, so you switch to plan view, foundation flow. So we are going to attach, and our foundation type shall be the pad footing. Okay, so assumption is that the soils are strong enough to accommodate that foundation type. Okay, in case your soils are too weak, you may be forced to use a raft foundation. Okay, and if it necessitates using pile foundation, okay, if the site conditions dictate pile foundation, you may find yourself using pile foundation. In case the stronger stratum is so deep, okay, you'll be what? You'll be forced to to use what? Pile foundation. So let's first turn off our grids, and so we are just left with columns. Yeah, before you carry out design for the foundation, you have to do foundation design settings as well. So we have allowable soil strength, ultimate factor. Okay, this factor here. So this factor is basically average of the dead load and the imposed load safety factor. Okay, it's the average of the two. Okay, so that's 1.35 plus 1.5 divided by 2. So you have to use the factors that you used in this design when you're setting up your load combinations. Okay, so we have 1.425. Okay, but I can explain it further why we are using the average. The reason is, so we shall put 1.4 to be safe. The reason is when we are sizing our footings, we rely on unfactored loads. Okay, however, the program here sizes the footings basing, so we rely on unfactored loads and check the resultant pressure against the safe bearing pressure of the footings. Okay, but this program will size the footings basing on ultimate loads and check the resultant pressure or the resulting pressure against the allowable pressure also multiplied by this factor. Okay, so allowable pressure converted to ultimate pressure. Okay, well, that's why we use the same safety factor, the average of the same safety factor that we adopted in the spark structure design. Okay, let's do 600 here, but of course it will not be the final. We shall design each footing. Then lean concrete or blinding shall do 50. Surcharge, this is the height of the soil backfilled onto the footing. Okay, minimum footing width is, let's just maintain that. Maximum bus spacing shall do 200. Concrete cover shall do 50. Minimum bar size 12. 12. Show grouped column labels, yes. Okay, that is it. So just say okay. Then after getting done with setting, after finishing the settings under parameters or building set out parameters, under foundation we have the allowable source trace and the subgrade coefficient. This is used in finite element, shall not finite element raft or foundation analysis. So you won't need it right now, but usually a factor that accounts for the allowable settlement of the what of the foundation, basing on the geotechnical investigations. Then allowable soil or stress is the allowable bearing pressure from your geotechnical investigation report. So here I have samples of the report. I have samples of the geotech reports on my desktop. Okay. So this is a sample of a geotechnical report, soil and geotechnical for the proposed classroom block. Okay. So in this report, usually executive summary will state, okay, the bearing capacities, the ranges of the bearing capacities at given depths. Okay, here we have capacities of ranging between 400 to 1900 kilopascals. Okay, at the depth between 1.2 to 2 meters. Okay, so then there's a recommendation. The report recommends a value of 407 kilopascals. Okay, uh, at a minimum depth of 1.2 meters from the reduced level or from the stripped level. Okay, so you could you should also go ahead and read through the report. Okay, bear in mind that you should do this before. You should read this report before starting your design. Okay, as the results or the outcomes of the report can affect other what design elements like the design aspects like concrete cover. Okay, concrete cover, choice of foundation type, and so on. It can also affect how the assumption you make when designing your ground beams. In that when the soils are too weak, you may be forced to design your ground beams as tie beams. Okay, as suspended beams actually. Suspended beams at the ground level, at the ground floor level. Because you cannot rely on the topsoil onto which the strip footing rests. This is some of the bearing capacity results achieved by the DCP test. Okay, these are trial pits at given depth. Okay, Okay, as you can see, this is the minimum value, 402. Alright, so that is the sample of the report. So if this was our site, I would maybe use a value of like 300 to design. If this report was for this site, unfortunately, they didn't avail us for this project. They didn't avail us with a geotechnical report. Okay, so I would put here 300. So for this, in case you're not given a report, you can make assumptions basing on the uh, existing reports on nearby sites in that locality. Okay. Yeah, so for where the site is, it is actually safe to assume a bearing capacity between 150 to 200. We shall use a value of 200 for this design. Okay. So what we shall do, shall highlight all columns, right click, then insert part base. Choose insert part base. Then okay. So leave the column to place leave the program to size the pad foundations for each column. Okay. Having done that, we are now going to we are not going to detail them the way they are, but we are going to group. Okay. We are going to look at closely related sizes, and we redesign those columns to adopt the same to have one uniform size. Okay, so we have 1.7 here. We have 1.6, 1.6, 2.2, 2.3, 1.9. We have so we have a minimum size of 1.6. Okay, so then a maximum size of 2.3. All right, so okay, so we are going to group all the footings having a size of 2.2 and 2.3 into one size, and that will be the maximum size of 2.3. Okay, so we shall delete this, this, this. Okay, let's leave this. Let's leave out 1.9. Okay, so we are going to redesign. This is 400 by 200, 400 by 200 column. So columns having the same orientation and size can be designed, their footings can be designed at once. Okay, so we're going to design these two. We're going to design for these two and these four also separately. So right click, insert pad base. Okay, you can see that the allowable, you have to confirm that the allowable stress is what is your preferred value. Okay, and from there just say calculate. Okay, so we have several checks. We have the soil stress check. Okay, soil stress check determines the size, okay, which is done automatically by the program. Then punching share check determines or governs the depth of the footing. Okay, same applies to shear. Then the moment check will affect the reinforcements provided. So we can see our shear stress here is 0.45 newtons per square millimeter, which is greater than the capacity, okay, of the concrete, which is 0.32, meaning the column is prone to punching through our footing, okay, which we don't want. So let's go and increase the depth here. So from 600, let's try 650. Still failing. 700 passes, okay, with the same size of 2.3 meters. Then the reinforcements required 16 at 150. Okay, so we are good to go. So I'm going to apply the same to these 4 columns, so that when we are detailing in AutoCAD, we provide them with one section. Okay, you can see. Then the other footing type is, we have this category of 1.9, 1.7, okay, 1.9, 1.7. We're going to provide them with 1.9. Then the rest 1.6. Okay, so a total of 6 footings. Then 1.6, there are 3 of them. So let's first delete this. Okay, so this is 400 by 200, 400 by 200, 400 by 200. So these 3, we are going to insert a typical footing. Okay, let's try a depth of 100. Okay, let's try 500. Fails. 500 fails. How about 550 passes? So 550 passes. The reinforcement we shall okay. Let's provide 600. Sorry, 600. Then we shall provide 816 at 175. Okay. Then okay. So shall do the same to these other ones. Okay, so shall do the same to this. Let's do this. These ones having the same orientation. We design them together. Okay, the size we shall force it to be 900. I mean 1900 millimeters. Tick calculate footing dimensions automatically. Okay, so we are done with that. Then lastly, this one. Okay, force it to be 1.9 with the same reinforcement details. Then lastly, let's design these 3. So these are all 300 by 200 and oriented in the same direction. Insert part base. Okay. So let's try 500. See whether it passes. It fails. How about 450? Still fails. 500 passes. Okay. You can see we have no size of 12 here. Have no size of 12. But when we go back to analysis, it's like we didn't select it under the rebar sizes at foundation level. Okay. Okay. So let's select these properties, calculate. Let's see how many 12s do we need. So if you choose to use 12, we shall have a spacing of 125. Can maintain 16 at 200. Okay, with our depth of 500, and that is it. So we've managed to achieve 3 types of footing: 1.6 by 500 deep, 1.9 by 600 deep, and 2.3 by 700 deep. Okay, so this will mark the end of our design stage. Okay, so we are done designing all structural elements. Okay, we are done designing all structural elements. So the next stage will be okay, the other thing I didn't talk about is that you can generate the reports for your footings. Okay, you can select all of them. You can start with this, the smallest. Then you choose maybe okay. Choose that one. Choose that one. Then this. So just interested in 3 types, and right click and say print purge design report, so that you have all the 3 types of footing into one report. Then you can export to Word for further editing and later appending to your general design report. Okay, so we have the 1.6 size, we have the 1.9 size here, and the 2.3 size as the last type. Okay, so shall do that later. Shall generate all the reports later on. Okay, so so that marks the end. So next time we shall look at how to produce drawings, and also how to generate all the design reports for all designed members.